Hi kidlets, this is your final notes video for the unit on the moon. A couple of necessary definitions as we talk about eclipses. Perigee and apogee have to do with the orbital position of something around a primary body, and that's when the primary body is something other than the sun. When it is the sun, it's called perihelion and aphelion. So in this case, perigee is when it's in its orbit and it's closer to the primary body, apogee is further away. And this is a consequence of having an elliptical orbit, that orbits are not perfectly circular. As we've said before, the ecliptic is the path of the sun on the celestial sphere, and nodes is when any orbit aligns with the ecliptic. So that would be the alignment of the moon on the orbit of the sun, or on the path of the sun. And aphelion, but you do need to know perigee and apogee right now because we're talking about orbital position in relation to the Earth. And that would be any primary body. So Jupiter's moons have a perigee and apogee, Mars's moons. Anything that's primary body is not the sun, we say perigee and apogee. And we'll see that this has consequences for solar eclipses, not necessarily lunar eclipses, although it would just make the moon look bigger or smaller in the sky. So lunar eclipse is the first type of eclipse we are going to talk about. Here we can see that looking at the orbital geometry, if we have the sun over here, we got the moon over here, this means that the phase of the moon has to be a full moon. So that is the only time you can have a lunar eclipse. We can see that we have this shadow of Earth that the moon passes into. The shadow created by Earth is far larger than the body of the moon, so the moon can actually stay in this shadow for a couple of hours, and that shadow is called the umbra. But we can also have an area of partial shadow, like this, called the penumbra. And when the moon is within that shadow, the moon appears completely red. So every object that produces light can produce an umbral shadow. The words umbrella and sombrero both come from the same Latin root word of umbra, which means shadow. So here we can see this shadow here, that's the umbra. The partial shadow would be the penumbra. So everything creates that. And we would see a complete lunar eclipse when the moon passes within that umbral shadow. So here again, penumbra way out here, and the umbra would be when the moon is within this area. So when it's within this period here, we would see a red moon. We would not see a red moon when it's here. And if you've ever seen a red moon without even knowing it, sometimes called a harvest moon or a blood moon, that is a lunar eclipse. You've probably seen it many times throughout your life. So here is looking at that orbital geometry again. We can see our full moon geometry, and here would be the period of total lunar eclipse. Here would be partial lunar eclipse. So when the moon is passing into Earth's shadow, it would appear as though slices are being taken out of it. We would see a period of increased darkness as it passes into the penumbra. We would see a period of reddening of the moon when it is completely within the umbral shadow. And we would see it appear to move in relation to the background stars. So the reddening is caused by the scattering of blue in the atmosphere. In Earth's atmosphere, obviously not the moon. If you were in open space, you wouldn't see it appear that way. This is just a phenomenon as seen from Earth. And these can last nearly up to 2 hours, which is far longer than solar eclipses, which are just a couple of minutes. And that's because the umbral shadow of Earth is larger than the moon, so it can take some time for it to pass within that. So as we'll see later on in this section, Eclipses occur with regularity, and these have been predicted for thousands of years. And there was a lot of power that was tied to being able to predict these. That is why this is called the Saros cycle. Saros meaning king, because kings use this to inflict fear over their people. So this is the list of upcoming lunar eclipses. So we can see upcoming in 2017, 2018, 2019, and we can see where the full and the partial eclipses would be. So next is solar eclipses. As awesome as lunar eclipses are, you've probably witnessed them your whole life and never knew that that's what you were actually looking at. Because half of the Earth can witness a lunar eclipse at any given point, whereas a solar eclipse is far more of a rare phenomenon. At any given point, only about 2% of the Earth can actually see a solar eclipse. And if you were in space looking back at Earth, this would be what you would see. You would see a shadow of the moon cast on the Earth. So here we still have an umbra and a penumbral shadow, but we can see that in this case, because this is a new moon is where a solar eclipse happens, full moon is where a lunar eclipse happens. In this case, the umbral shadow falls on the Earth. It's not the moon passing within it, it's the moon causing it. So it's the umbral shadow of the moon cast on the Earth. And if you were within this sphere, you would experience complete darkness. So here we can look at a couple of geometric pictures here. So if you were within this, the penumbra of the shadow of the moon, you would see a partial eclipse, which would actually look like a bite is being taken out of the sun. And this is the geometry of that. It's because the moon would be crossing in front of the sun. Now remember that since this is a new moon, this happens during daytime. You can see that this would be noon. So this would be happening during daytime. So if you were within this sphere, you would experience complete and total darkness. If you're in the umbral shadow, this would be what you would see. So you would see just the ionized outer layers of the sun. Here's your geometry. The sun is behind the moon. And an annular eclipse, we'll talk about in just a second, is where you can still actually see the outer layer of moon. And that is because of the perigee and apogee and the location of the moon within its orbit. That would take it closer to us and further away and not entirely blocking out the moon. So here again is our geometry of a solar eclipse. So we can see that this is a new moon. And again, here would be our umbra, and this period here would be our penumbra. So only if you were located right here at this teeny spot would you experience a complete and total eclipse of the sun. So the reason for that has to do with angular diameter. Right now, at this current phase of Earth's history, the moon and the sun appear the exact same size in the sky, which means that if you were to look up and you were to actually measure them, they occupy the same angular diameter. In this case, it's about a half a degree. So we've already said that your pinky is about a degree of sky. Half of that, if you were to raise up your pinky, about half of the width of your pinky would block out the moon and the sun, which is the reason this is important in terms of historical positioning in the solar system, is that we're losing the moon at a rate of about 2 centimeters a year. So in distant Earth's history, it was too close to have a solar eclipse. And in the future, it'll be too far to have a solar eclipse. So we exist in this perfect period of Earth's history where the moon is located at a perfect distance from us to completely block out the sun. So this distance is exactly, the distance between Earth to sun is exactly 1/400th of the distance from moon to sun. And the size of the moon is exactly 1/400th of the size of the sun. So that's a perfect fraction, which is what makes eclipse geometry so amazing. We just live in a perfect time of history of the Earth to actually have solar eclipses, and we're the only place in the solar system we've ever observed that has that phenomenon. So here we can see what angular diameter is. So if we were to measure the actual space this takes up in the sky, this would be about a half of a degree. And this should be the degree mark there, I apologize. So both the moon and the sun appear to occupy about a half a degree of sky. So here we can see that looking at the path of the moon on the Earth, that it would create this path of darkness. And this is taken from the International Space Station. This is actually looking at the path of a total eclipse on Earth. So if you were within that, you would experience complete darkness. But remember that we're rotating, and the moon is orbiting around us as we're rotating. So we would see, if you're looking at it from space, you would actually see the path over time. Now, if you were observing an actual eclipse, this is a time lapse of what you would see. So you would see what would look like the moon traveling across the sky, and within a matter of minutes, right here would be probably only about 15 minutes, you would see what would look like a bite being taken out of the sun. It would be completely blocked out, and then the bite would move to the other side. So here, looking at the sun during a total eclipse, we can see these ionized outer layers of the sun. Solar eclipses are really important for giving us information about the sun that can only be seen during solar eclipses. And here again, we can see that shadow of the moon on the Earth's surface. So a couple of solar eclipse definitions. We have partial, which is when only part of it is blocked out. We have a total, when all of it is. But then really important is annular, which does not mean it happens annually, and it is not the same as partial. Partial is when literally it looks like you have part of the moon that is not entirely blocked out, to where it might look like this. So you'd have a big chunk blocked out, but the rest wouldn't be, so it'd look like a bite. That is not the same as annular. Annular is entirely a consequence of that orbital dynamics of perigee and apogee. So when the moon is at apogee, or further in its orbit, it is too far away to completely block all of these outer layers of the sun. So it would literally look as though you had a ring of sun around that outer layer of moon. And solar eclipses are important because this allows us to understand the phenomenon of helium in the sun. We know that there are fusion processes within the sun that combine like protons of hydrogen and have a production of helium with a byproduct of light energy and heat. It allows us to observe the corona, which are these outer layers of the sun, which can be really damaging to us. These burn at 1,000,000 degrees. Release powerful gamma rays and x-rays, and it allows us to measure that. For some reason, there is this heating of layers further away from the sun, so the surface that we see is actually the coolest layer, and the outer layers are the hottest. It allows us to observe the role of magnetic fields and magnetism within the sun that causes sunspots. So this is an image of looking at the actual angular diameter of perigee and apogee. So we can see just how big they would look. So at perigee, the moon would actually appear about 13% larger than when the moon is at apogee. And we can see that those are a much greater distance away as well, about 40,000 miles, or about 90,000 kilometers. So looking at a process of an eclipse, we can see here would be the sun before it is eclipsed. That eclipse is beginning on the right-hand side. As the moon moves in front, we can see that bite. Here we can see a large bite. This would be when it is just about in totality, and complete longer exposure totality images would reveal those outer layers. So here we can see these purple. These would be our prominences, our flares, and we can also see these outer layers of chromosphere and corona, which are above the outer layer of the photosphere of the sun. And it's the only time we can see these, because the photosphere is what we see as yellow, because that emits invisible wavelengths. The chromosphere and the corona are far hotter, so they are only seen in UV and gamma ray images. So we can only see these if the sun is blocked. And when we're looking for extrasolar planets, we have to block out the light of the parent star, so they simulate eclipses. This is actually what's done, is they block out the light from that star to be able to see if there are planets around it. So we will look at this image in class. You can actually follow this link for the GIF as well, and you can see the eclipse shadow moving across northern Africa. So eclipses are a pretty amazing thing, and we know that we have new and full moon every month, and we know that eclipses only happen when we have a new and full moon. But we don't have eclipses every month, and that is because the orbit of the moon is tilted in respect to the plane of the ecliptic. It is about 5 degrees off. So essentially, our plane and the plane of the moon's orbit do not perfectly align. So we can only have eclipses when they do. So here we can see that the umbra of the moon, and in this case the umbra of the Earth, they do not perfectly align. During eclipse season, when we have the conditions favorable, you can see that the umbral shadows do align. We call that crossing a node. So here, daytime would obviously be a solar eclipse, nighttime would obviously be a lunar eclipse, and here we can see the path of both the moon's orbit and the ecliptic And in this case, this is not favorable for an eclipse because we can see the new moon and the sun, so it doesn't entirely block it. We would only have eclipse conditions when it is the right moon phase, so new or full, and the moon is on a node. And a node is where the moon's orbit crosses the plane of the ecliptic. So those are the conditions necessary for an eclipse, is that you have to have the correct moon phase and you have to have the moon that is crossing a node on the ecliptic. And it's off by 5 degrees. This should say 5 degrees, not 50. So that should be the degree symbol. So I'm just looking at some numbers here. We can see that the average lunar distance is about 384,000 kilometers. The eccentricity of the ellipse is about 0.05, so it's very slightly elliptical. So just for some perspective, a perfect circle has an eccentricity of 0, a straight line has an eccentricity of 1. So this is just slightly larger than 0, so it's only slightly elliptical. But we can still see that there are measurable differences between perigee and apogee. So perigee significantly closer than apogee is. So here we can see the comparative sizes of perigee and apogee, both of the sun, or perihelion and aphelion, when Earth is in those positions, and perigee and apogee of the moon. So we can see when the moon is at its closest, it's about 13% larger than when it's at the furthest. And when Earth is in its closest path around the sun, at perihelion, you can see it is much larger than when we are at aphelion. So when Earth is near perihelion, so we are here, so we're closer, and the moon is near apogee, so it's further, we don't have the conditions to completely block this layer of sun, and you can see it appears to have an orange ring, not those layers of solar atmospheric layers surrounding it. So this image is interesting because we have one side of the image where we can see outer layers of sun. We can still see part of the solar disk that would be seen in yellow or orange. So here we have annular, but on this side it's completely blocking. So it's an almost total annular eclipse, which is a very, very rare event. So it's essentially half and half. So on this side it's blocking so we can see some of those gases. But when we can still see part of the solar disk, that means that the orbital geometry is not entirely perfect to completely block the sun. So when the moon's distant, the moon is too small to completely block it. And here we can see just some images showing the time lapse of that. And here we can see pretty clearly that the disk of the sun is not entirely blocked. So here's the diamond ring effect shown when the moon is near totality, when it's almost blocking the sun. This would be about the last glimmer of light you would see. And remember that this is taken during broad daylight, when you have, full sky of sun during, high noon. And this would make the sky completely black. So imagine, if you're early people prior to internet, and your ruler says that he's going to block out the sun and make the sky gods take a bite out of the sun, and this happens and the whole sky is black, it's easy to see how fear was really instilled by just being able to calculate the frequency of eclipses. So here we can really see these prominences, which are essentially ripped solar flares that do not connect back down. These can extend up to 3 times the diameter of Earth. So these are huge, and this is when we can really see those. The chromosphere is the layer above the photosphere. It is significantly hotter. And solar eclipses are the only times that we can see these layers of the sun. So looking at some frequencies of solar eclipses, we have an upcoming that is going to be visible in the U.S. So in 2017, we have one in July in the Pacific. We have one in August in the Pacific. And if you by chance ever have the opportunity to witness a solar eclipse, it is definitely a bucket list item. When it is visible over North America, I highly suggest you take the time to do it. This is a once-in-a-lifetime opportunity, but really important to never look directly into the sun. It's actually a bit more dangerous to look during a solar eclipse. They make eclipse glasses now. I remember there was a solar eclipse that was visible when I was in elementary school, and they made us do something like this, and there's another way where you can look in a bucket of water. But if it were me, I would definitely want to be able to look directly at it, so they make eclipse glasses. There are whole vacation cruises and packages built around eclipses because it's a pretty amazing thing. So we know that eclipses occur in a cyclic pattern because we can predict when the moon is going to be on those nodes, but it also occurs at regular frequencies all over the planet. So there is a pattern in which it's going to hit in terms of time and location. And here we can just see some upcoming predicted eclipse paths. And here is what the Saros cycle would look like. So here are months of the year, here are years, and we can see that these occur with regular occurrences all over the planet. Thank you guys. I will see you in class.